All right, so in chapter 6, what we're going to be doing is taking a look at different types of compounds that can form when particles combine together. And specifically, what we're going to be looking at is what actually holds these particles together, right? So overall in chapter 6, we're going to be taking a look at bonding, right? And we can think of bonding as just generally, as an analogy, as the glue that holds particles together. And these particles could be things called ions, they can be atoms, together in different types of compounds. All right, and then what we're going to be focusing here on is we're going to look and we're going to look at and use our Lewis symbols to help us. To help predict what's going to happen or the type of bonding that's going to occur. Right, and we saw Lewis symbols at the end of the previous chapter, chapter 4. All right, so that's going to be the general gist of chapter 6. In the first half of the chapter, we're going to be taking a look at a type of glue or a type of bond known as ionic bonding. And in the second half of the chapter, we're going to take a look at another type of bonding known as covalent bonding, which we find in compounds known as molecular compounds. So we can say that chemical bonds are formed when atoms either lose, gain, or share electrons. And specifically, the types of electrons we're going to be looking at here are going to be the valence electrons, which are the outermost electrons in an atom. So these chemical bonds, the glue that holds your ions or your atoms together, these are formed when these atoms lose, they gain, or they share electrons, and the type of atom that we're dealing with is going to dictate whether it will lose, gain, or share electrons. What's going to be the driving force for the loss or the gain or the sharing of electrons is stability. Okay, so stability drives or dictates bonding. Things want to be as stable as possible. Okay, so your chemical substances want to be as stable as possible. And the underlying principle behind bonding and achieving stability is something known as the octet rule. All right, and the name here, octet, kind of tells you a little bit about what it involves. And when you hear the term rule, especially at the introductory level, you may think, well, you know, these are things that always have to be followed. But the reality is there are lots of exceptions to the octet rule. So there are exceptions. We're not going to worry too much about the exceptions in this class, except maybe one important one. So we can still use the octet rule as our guiding principle for describing bonding. And the octet rule states that atoms will lose, gain, or share electrons. And again, we're looking at valence electrons, so that they have a total of 8 valence electrons, right? That's where the term octet comes from. And in most cases, what this is going to involve is the atom trying to be like the nearest noble gas in that particular period, right? So the atom wants to be like, so the atom wants to be like the nearest noble gas. And if you remember from chapter 4, these noble gases all have a full valence shell, right? The outermost shell is completely full, which makes them very stable, right? So that's the whole idea behind this octet rule and achieving stability. And your atoms can become more stable. They can become, in terms of their electrons now, like the nearest noble gas by either losing, gaining, or sharing electrons. And there are two types of bonds that we're going to see. We talked about, we introduced at the beginning, ionic bonds. And these are bonds that are going to be formed when metals lose electrons to form positive ions, and your nonmetals gain electrons to form negative ions, right? What you end up happening then is you have positives and negatives right next to each other. So we have the attraction between these ions. Right, that's what an ionic bond is, just the attraction between a positive ion and a negative ion. So what we have occurring here is there's going to be a transfer of electrons from the thing that's going to lose it, which is the metal, to the thing that's going to gain it, which is the nonmetal. Right, so those are two really important characteristics of ionic bonding. First of all, it has to do with the electrons. We have the transfer of electrons. And then the second thing, important characteristic, is the types of elements involved. So we have metals and we have nonmetals. And that's very different than a covalent bond. And in a covalent bond, what we see occurring is that there's the sharing of electrons between nonmetals. All right, so it's very different than ionic bonding. So here we have the sharing of electrons, and we only have nonmetals involved in this type of bonding. So those are two really important differences between these two main types of glue that we're going to see in this class. All right, so this diagram here kind of illustrates the difference between them. I'm just going to draw a line down the middle to separate them. So on the left side, we have ionic bonding, and what we see occurring is that there's a transfer of electrons. The metal loses electrons, and the nonmetal gains electrons. And we end up forming the metal. When it loses an electron, forms a positive ion, and the nonmetal, when it gains an electron, forms a negative ion, and the attraction between them is what that ionic bond is. On the right side here, we have our covalent bond, and here we have the sharing of electrons. All right, so we have sharing of electrons between nonmetals. So the type of glue occurring here is that keeps these two elements together is slightly different. So one thing that you really want to keep in mind, always keep in mind when it comes to bonding, is that we never mess with, or we never lose, gain, or share the protons. Okay, the proton stays the same. Right, because if you change the number of protons, you change what that element is, and you can't do that in chemistry. The only thing that we can lose, gain, or share are going to be our valence electrons. So always keep that in mind. We never ever change the number of protons when it comes to chemical reactions and chemical bonding. Okay, so we can take a look now at some examples of where these positive ions can form. So the first thing to keep in mind is the types of elements that form positive ions, and these are going to be your metals. And the metals that we're going to look at again here are going to be in the representative or the main group elements, group 1A, group 2, and then group 3. So for example, let's just choose sodium. So sodium has the elemental symbol Na, and the electron configuration or electron arrangement for sodium is 2, 8, 1. Right? So it's got one valence electron. And in order to, so we can, what we can do then is to draw the Lewis symbol for this. Just going to have one valence electron. So in order for sodium to become more stable and follow the octet rule, okay, it's going to want to, so it wants to lose that one valence electron. So when it loses that one valence electron, all right, what we end up forming now is a positive ion. Right, and an ion is just something that has a charge on it. So it's a charged species. And because we've lost just one electron, we've taken away now one negative charge, we end up with an overall positive charge on that sodium ion. All right, so we call these positive ions that are formed, we call these positive ions, give them a special name, we call them cations. All right, cations are positively charged. And your metals are going to form cations when they lose electrons. All right, and we looked at sodium as an example of that. All right, so this is just another example of sodium losing its one valence electron. All right, so notice here sodium is going to have 11 protons. We don't mess with the protons, so it stays the same. So we start off with 11 positive charges, and we also have 11 positive charges at the end. At the beginning, we have our neutral sodium atom, so we have our 11 electrons, 11 negative charges. When we lose that one electron, now we end up with 10 negative charges, right? So if we overall look at the charge of the sodium atom that we start with, we have a charge of 0, and when we lose that one valence electron, we end up with a charge of 1+. All right, so that's how we can make a little bit of mathematical sense of the of the charges. So a couple things, or one thing to keep in mind, sometimes you'll see sodium just with a positive, or sometimes you'll see Na positive 1. All right, the 1 is understood to be there. You don't need to put the 1 in. If you just put positive, that would suffice. So there are some trends that we're going to see in the periodic table when it comes to determining the charges on the metals, and we'll just state the trends as follows. So for the representative metals, okay, so this would be groups 1, the metals in groups 1, 2, and 3. All right, the quick way to determine the charges on those metals when they form ions. The charge on the metal ion is simply equal to the group number. All right, so for instance, we just looked at sodium. Sodium's in group 1, so it forms a charge of +1. Remember, metals form positive charges when they form ions because they lose electrons. If you look at something like calcium, calcium's in group 2. Right, this will form a charge of +2. And if you look at something like aluminum, aluminum's in group 3. Right, so then it will have a charge when it forms an ion of +3. Right, so that's a really good and useful shortcut you can use to determine the charges on your representative metals. All right, let's take a look now at the other end of the spectrum, our negative ions. Our negative ions is a special name that we give to these. Negative ions are also called anions. So anions have a negative charge. Right, and these form when your nonmetals gain electrons. To form these anions. And again, the octet rule is going to be our driving force for this. So for example, right, if you look at chlorine, okay, chlorine is in group 7. So Cl is going to have 7 valence electrons. So we have 1, 2, 3, 4, 5, 6, and 7. That's your Lewis symbol for chlorine. It wants to gain 1 more electron. So it wants 1 more. To have 8, right? And that's going to be our octet rule. So when it gains that 1 electron, it now ends up with 1, 2, 3, 4, 5, 6, 7. We'll draw the 8th one in here as a red one. All right, now it's got 1 more electron than proton than it started off with. So it ends up with an overall negative charge, or a -1 charge. All right, and the reason why it wants to do that is because it wants to become more stable by following that octet rule. All right, so again, we can make sense of the overall charges, some mathematical treatment of this. If you start off with your chlorine atom, your neutral atom to begin with, it's got 17 protons. At the end, it's still going to have 17 protons. All right, originally your chlorine atom is also going to have 17 electrons. When it gains 1 more electron, now it's going to have 18. So if we look at our charges, all right, our atom here at the beginning is going to have 17 protons, 17 electrons. Overall charge is 0. When it gains 1 more electron, now it's going to have 18 electrons. It still has 17 protons. The overall charge now is 1 minus. Right, so we end up with Cl with a minus charge. We can use that as our example, and we can also use it as a template for a shortcut for determining the charges on the nonmetals. So the charges, so let's just say shortcut here. For determining charges on the nonmetal ions. Okay, the charge is simply equal to the group number minus 8. Okay, so for example, we just looked at chlorine. All right, chlorine, as we said, is in group 7. So the charge on the chlorine ion then is equal to the group number 7 minus 8, which gives -1, right? So we end up with Cl with a minus charge. Similarly, if you look at something like nitrogen, right? Nitrogen, if you look up on the periodic table, it's in group 5. So the charge then on the nitrogen ion is the group number 5 minus 8, which gives -3. Right? So we end up with N with a -3 charge. And we can use that that general rule for determining, it's a shortcut for determining the charge on our non-metal ion. It's the group number minus 8. All right, so there's names that we give to these ions that are formed as well. The name, when a metal forms a cation, we don't change the name of it. The name actually stays the same. All right, so you'll see here the sodium ion is just called sodium. Potassium is called potassium. Calcium is called, the calcium ion is called calcium. Barium is just the barium, etc. So the names of the metal ions don't change. However, the name for the non-metal ion does change. All right, so for instance, if you look at the examples that we looked at before, so chlorine, for instance, is the atom. When it forms a Cl minus, so it gains an electron. When it forms a Cl minus, we call this now, this is not chlorine, this is called chloride. So it has that IDE ending. All right, similarly, we looked at the nitrogen before. All right, so nitrogen, when it forms an ion, right, it is going to gain 3 electrons. And it forms N with a -3 charge. N with a -3 charge is not nitrogen. Now it's the negative ion, and we call it nitride. All right, and then similarly, very common one you'll see a lot is oxygen. All right, oxygen, when it forms an ion, because it's in group 6, it's going to want to gain 2 electrons, and it'll form O with a -2 charge. That's not oxygen anymore. That ion we call oxide. Okay, so the trend here is, when you look at all of these, is that all of these non-metal ions have the same ending. They all end in IDE, every single one of them. Okay, and that tells you that you're dealing with an ion, not a neutral atom. All right, so we can say the names for the non-metal ions, the anions, in other words, negatively charged, all end in IDE. Okay, and that's important to note because you want to make sure that you use the proper terminology when it comes to referring to, and we'll use this in the next section when we look at naming our ionic compounds.